Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. My name is Nuridina Hanan binti Muhammad Zaim. Today, I am incredibly excited to present my video project about relations, functions, and graphs. We begin with part 1, Introduction to Relations. Mathematically, data in computer systems rarely exist in isolation. If we have two arbitrary sets, set A and set B, their Cartesian product, denoted as A multiplied by B, represents the set of all possible ordered pairs where the first element is from A and the second is from B. Formally, as defined in Kenneth-Rosen's discrete mathematics and its application, a binary relation R from A to B is a subset of this Cartesian product. We express this as R is a subset of A multiplied by B. Let's look at the concrete, undergraduate level computer science example shown on the right of the slide. Suppose we have a set of server users, set A equal to U1, U2, and a set of target host servers they might access, set B equal to H1, H2. The complete Cartesian product A multiplied by B contains exactly four ordered pairs, U1, H1, U1, H2, U2, H1, and U2, H2. If a system administrator grants only user 1 permission to access host 1 and user 2 to host 2, our actual active access relation R is the mathematical subset, U1, H1, U2, H2. This simple mapping forms the fundamental logic of all system network access controls. Now, let's address the core problem in software engineering. Why do systems fail? Database queries lag or data get corrupted? The root cause is often bad structural mapping. When software engineers design a database or system permissions without calculating the formal mathematical relations, it leads to massive issues like data redundancy, update anomalies, and security vulnerabilities. By studying relations, we are not just looking at numbers, we are solving the root cause of systematic software design flaws by enforcing mathematical constraints before a single line of code is written. In software engineering, relations on a single set A are classified according to specific algebraic rules. Analyzing these properties allows us to optimize compilers and safety model network handshakes. There are three core properties we must evaluate. First, reflexivity. A relation R on a set A is reflexive if every single element relates to itself. Mathematically, for all A belongs to A, the pair A belongs to R. In computer systems, identity checks, directory pathways, and reflexive database self-joins rely on this property to guarantee integrity. Second, symmetry. A relation is symmetric if a relationship in one direction implies it also exists in the reverse. Formally, if AB belongs to R, then BA belongs to R. This is the exact method used to program peer-to-peer connection protocols or simple bidirectional friendships in social media networks. Thirdly, transitivity. A relation is transitive if connections can cascade across a sequence of elements. If A relates to B and B relates to C, then A must relate to C. This property is absolutely vital for transitive closure algorithms, computing routing tables in computer networking, and executing security permission inheritance trees. This brings us to part 2 of our presentation, functions as special relations. How exactly does a function differ from a standard binary relation? A function f from a domain set A to a codomain set B is defined as a relation f is subset to A multiplied by B that must satisfy a strict uniqueness constraints. This constraints dictates that every single element in the domain A must map to exactly one unique element in the codomain B. Formally, as written on the slide, if xy belongs to f and xz belongs to f, then y must equal z. This means that while a standard relation allows an input to map to multiple outputs, a function strictly prohibits this. In computer programming, this restriction is what ensures determinism, guaranteeing that when you call a function in code with a specific input, it will always return the exact same output without runtime ambiguity. Let's go through the step-by-step verification calculations to evaluate whether a given relation qualifies as a mathematical function. Let our domain set be A equal to 1, 2, 3 and B equal to x, y, z. Look at case A on the left. We have a relation R1, 1x, 2y, 3y. Let's run our verification algorithm. Step 1, we check if all elements of domain A are mapped. Yes, 1, 2, and 3 are all present as first elements in our pairs. Step 2, we check the uniqueness constraints. Does any domain element map to more than one target? Element 1 maps to x, 2 maps to y, and 3 maps to y. Each maps to exactly one target. Note that codomain sharing is allowed, both 2 and 3 map to y. Therefore, R1 successfully passes verification and is a valid function. Now, look at case B. On the right, we have relation R2, equal to 1x, 1y, 2z. Step 1. We check the domain elements. Element 3 in domain A has no mapping value whatsoever. This is our first violation. Step 2. We check uniqueness. Element 1 is mapped to both x and y. This directly violates the uniqueness criterion because 1x belongs to R2 and 1y belong to R2. But x not equal to y. Consequently, R2 fails verification and is not a function. In a real software system, executing R2 will cause critical, unpredictable crash errors. Moving deeper, functions are classified into distinct taxonomies that dictate how they can be used in software architecture. First, we have injective, or one-to-one functions. This constraint ensures that distinct domain items always map to distinct codomain items. In system engineering, this mathematical rule is what guarantees that a primary key index in an SQL database or a unique resource identifier is perfectly unique, preventing data collection. Second, we have surjective or onto functions, where every element in the codomain set B must be mapped to at least once. This is extremely useful in server load balancing, partitioning, and hardware allocation algorithms to ensure no resource is left idle. Finally, a bijective function is both injective and surjective. This creates a perfect one-to-one pairwise correspondence. Because bijections are completely reversible, they form the mathematical heart of secure cryptography, such as RSA encryption schemas and reversible compression algorithm. This brings us to part 3, graphs as special relations, which is the final measure discrete structure requested. To represent complex systems like physical networks or social media connections, computer scientists use graphs. Formally, a graph G equal to VE consists of a set of vertices V and a set of edges E. And H connects two vertices together. This H set E is quite literally a direct binary relation defined on the set of vertices V. Therefore, E is a subset of V multiplied by V. We categorize these relations into two distinct graph architectures. In directed groups or digraphs, the relation is asymmetric, and H exists as an ordered pair UV, meaning you can only travel from origin node U to target node V. Think of this as a follow relationship on Twitter. In undirected graphs, the relation is perfectly symmetric. If UV belongs to E, then VU belongs to E automatically. This represents bidirectional relationships like a friend connection on Facebook. Let's demonstrate the exact algorithmic process that a computer uses to store and analyze these graph relations. Machines do not see graphical drawings, they process mathematical structure. Suppose we have a small network of 3 servers set V equal to S1, S2, S3. Let's define their connections as a formal relation set. R equal to S1, S2, S2, S3, S3, S3. Looking closely at this relation set, we can analyze its mathematical properties. It is not reflexive because we do not have S1, S1. And it is not symmetric because we have S1, S2, but not S1, S2, S1. To store this relation in memory, a computer constructs a binary grid known as adjacency matrix as shown in step 2. The rows represent the origin nodes and the columns represent the target nodes. For every pair, S1, Si, S0 present in our relation set, the computer writes a binary 1 in cell M row. Mij, otherwise it writes a 0. Following our relation, cell S1, S2 gets us 1, cell S2, S3 gets us 1, and cell S3, S3 gets a 1. All other cells are filled with 0. This simple mathematical matrix allows software algorithms to instantaneously compute data path, verify connections, and query relationships in linear time. In conclusion, we have explored how relations, functions, and graphs are deeply interconnected. By framing these discrete concepts within a strict mathematical framework, computer scientists can transition from chaotic or unorganized data to elegant, predictable, and scalable software systems. As summarized on this slide, databases are structured entirely on relational set theory. Functions enforce the mathematical constraint of uniqueness to guarantee error-free, deterministic code execution. Graph map physical networks and social media structures using binary adjacency relations. Ultimately, empirical software engineering shows that designing systems around this format, mathematically proven frameworks drastically reduces logical bugs, ensuring resilient, enterprise-grade software architecture. This is the references and citation attributions. Thank you very much for your time and attention.